everyone. And Doug Shinneman and I are co-presenting, and he's going to advance the slides for me. So I think this will all go smoothly. We really appreciate the opportunity to talk about aspen in the Great Basin today. Doug and I are both based at USGS in Boise, Idaho, and have focused our aspen work largely in the Great Basin. Next slide, Doug. We are going to talk about some of what has already been discussed today, but we're also going to focus on fire. We're going to start by discussing recent aspen fire trends and a few general concepts about aspen fire ecology. And then Doug will provide some research findings about key aspen climate relationships, provide examples of some disturbance interactions, and then talk some about management challenges that aspen face. Here we can see the North American distribution of aspen and its sparse and isolated distribution in the Great Basin in the middle of the screen. Zooming in, we can see that these sparsely distributed aspen ecosystems comprise a small amount of the Great Basin, only about 1 to 1.5% of the total area. However, pure aspen and mixed aspen conifer forests actually comprise 2/3 of all montane and subalpine forests in the region. So, and you can also see the substantial recent fire history in the Great Basin, with over 23 million acres burned in the region between 1984 and 2018. In fact, the area burned in Great Basin aspen forests has increased really significantly over the last 35 years. About 295,000 acres of aspen habitat has burned during that period, which equals about a fire return interval of about 220 years. But if these trends continue, we're going to expect to see fire-free intervals decrease into the future. Aspen's a fire-adapted tree species, so the question is, will aspen benefit from fire? And the answer is it depends. There are multiple factors that could impact these relationships. The first being the relative fire dependency of an individual aspen stand. Aspen aren't all created equally, as has been a theme so far. Interactions with climate, such as post-fire climate conditions that may affect aspen regeneration. Interactions with other disturbance agents, such as drought and excessive herbivory. And then also interactions with competitive species, such as conifers, but also those that might benefit from fire, such as non-native grasses. Funny to be doing this halfway and halfway. So here we are. So we're going to spend a little time talking about some basics of aspen fire ecology. Most fires occurring in aspen can be considered high severity, as aspen are easily killed by fire, especially in mixed aspen conifer stands where crown fire is common. Aspen's considered highly fire adapted, in part because it's often a prolific resprouter following fire. Vegetative suckering from roots of aspen clones is its most common method of regeneration in the West. But as Paul mentioned, sexual reproduction from seed is becoming more and more acknowledged. Aspen stands are often seral to other tree species, especially conifers that can gradually replace them in the absence of fire. And so many aspen stands are considered fire dependent. But stable aspen stands that don't depend on fire are not uncommon, especially when conifer competition is rare. So I want to talk a little bit more about cereal aspen stands. An idealized successional trajectory for cereal aspen includes 4 basic principles. A stand replacing fire occurs, as in the upper left, and after which young and often even-aged stands of aspen develop quickly. And then as these aspen cohorts age, they gradually provide conditions favorable for recolonization by shade-tolerant conifers. And then as the older stands become increasingly dominated by more mature conifers, the aspen regeneration will decline and the stands become more fire prone and repeat that cycle again. This can create a very dynamic and spatially complex mosaic of aspen and conifer across a landscape. In contrast, stable or persistent aspen, which again we've talked about some already today, are generally considered self-sustaining. And so the rate of mortality of older trees doesn't exceed the rate of successful recruitment of younger trees. These are often pure aspen stands with multi-cohort structures throughout the stand in which there's a negative exponential relationship between tree age and density. So far more younger trees than older trees. This can happen as in number 1, through continuous or episodic recruitment, such as canopy gap mortality caused by insects, disease, or aging trees. However, stands may also experience and recover from more extensive overstory mortality, as in the drought or insect-killed stands represented by number 2, or through a stand replacing fire event, as in number 3. So it's not a matter of no disturbance in persistent stands, but rather a stand can persist through multiple generational rotations without major disturbance events. And we actually looked at this concept of stability versus cereal stands in northern Nevada across 3 mountain ranges, the Santa Rosa Mountains, the Jarbidge Independence Range, and the Ruby Mountains. Pure aspen stands are common in these ranges, with upper montane conifer cover largely absent or rare, with the notable exception, the central Jarbidge had a lot of subalpine fir forests as well. In that project, we sampled 101 aspen sites using various techniques. And Doug now is going to take over and talk about findings from that work and some other aspen research we've been focusing on.
Okay, thank you, Susan. So one of the key findings from that research was that age and size class distributions suggest that aspen are largely self-replacing and stable in these mountain ranges. The figure at left indicates that aspen stands range from quite old to relatively young, based on the oldest trees dated in the stands. However, the figure at right shows that ample reproduction was occurring with negative exponential relationships between age and density across each mountain range and for the study area as a whole. So these age class distribution patterns were strongly consistent, even among different aspen forest types. In other words, whether we group them by pure aspen, riparian aspen, aspen conifer mix, or what have you. And these relationships were also commonly exhibited among individual stands as well. So despite finding very little evidence of fire in any of these stands, aspen are apparently self-sustaining at the landscape scale and mostly at the stand scale as well. Similar findings have been reported elsewhere in the Great Basin, but not in all cases, especially studies that focused on locations where conifer competitors were more abundant. And due to the absence of major fire events that would have produced pulses of aspen regeneration through time, climate was clearly correlated with aspen establishment over time in these stands. And that included both temporally lagged and contemporaneous relationships. For instance, the figures at right illustrate how variability in the Palmer Drought Severity Index, which is an index of relative dryness or moisture availability, and maximum spring temperatures clearly align with the variability in aspen establishment density, the lower part of that figure. And that's apparent because the climate records have been realigned 5 years forward and 1 year back, respectively, relative to the aspen establishment density by year in that bottom part of the figure. Other climate variables that we studied that aren't shown here had similarly timed relationships with aspen density by year as well. And we think this suggests aspen clones are producing and storing carbohydrate reserves during more favorable, especially wetter climate periods. And subsequent drier and warmer conditions are promoting canopy mortality, which then induces suckering and sucker growth, in part by allowing more sunlight to reach the forest floor, reduction of apical dominance, and because the clones are able to capitalize on those stored energy reserves. Of course, other factors such as browsing of young aspen by wild and domestic ungulates could also affect aspen regeneration. In fact, we found a significant difference in the proportion of suckers reaching recruitment height between plots classified as either low or high browse in our study area. And again, recruitment height, it's often considered to be around 2 meters because that's generally tall enough for a young aspen to be less susceptible to mortality from browsing. However, I should point out that excessively browsed stands were relatively rare among our sites, and they effectively had a negligible impact on landscape scale rates of recruitment. In another study, we sampled aspen stand regeneration in various locations that have burned 5 to 15 years previously throughout the northern Great Basin and Rocky Mountains. And the results from statistical models from this research strongly suggested that winter precipitation had positive effects on density of both overall regeneration and recruitment size aspen. The early winter precipitation ratio had the largest effect size, and this is a metric we developed that represents the ratio of average early winter precipitation during a 5-year post-fire period to the long-term 30-year average. In other words, was the site wetter or drier than average during the post-fire period? And similar to the previous study, indicators, whoops, go back a sec. Indicators of browsing were also important and had a negative effect on recruitment densities. So studies like this suggest that winter precipitation may be particularly important for aspen's persistence, especially under climate change, and particularly in the Great Basin, which receives most of its precipitation during winter months. There's been a marked decline in snowpack across the western US over recent decades. And a recent study predicted that under projections of future warming, there will be substantial reductions in annual maximum snowwater amounts in the northern Great Basin. And this could have consequences for aspen stands that depend on melting snowdrifts for water subsidies during the generally dry growing seasons in the Great Basin region. These aspen stands are often called snowdrift dependent or snow pocket aspen. So numerous studies are also predicting increasing fire activity in the western US under climate change over the next few decades. For instance, researchers found that the burned area in California increased by just over 400% over the 47-year period shown in that top figure, and that this increase was highly correlated with atmospheric vapor pressure deficit, a measure of aridity. The plot below shows that maximum temperatures from March to October have increased by nearly 2 degrees Celsius over the past 120 years, which corresponded to a 13% increase in that vapor pressure deficit measure. And given these relationships, we should expect continued increases in fire activity in the future based on climate projections. So one way to explore hypotheses about the future of aspen is to use disturbance and succession models that simulate interactions between changing climate and fire regimes. And I can only quickly summarize a few examples here. In one study, my colleagues and I developed projections that suggested more fire under a warming climate might result in aspen replacing some conifer forests at higher elevations, where climate was more likely to remain suitable, but that fire could hasten aspen's demise at lower elevations, where climate scenarios suggested conditions would become increasingly less suitable, especially for regeneration. In another modeling study, we found that by simulating shifts in snowdrift water availability, that might be expected from a hotter climate, snowdrift-dependent aspen stands are unlikely to receive adequate growing season soil water subsidies to support regeneration rates necessary for replacement of aging and dying overstories. And in addition to modeling, there are other reasons to think that low elevation aspen stands in particular are at risk due to changing climate and fire regimes. Great Basin rangelands that border low elevation aspen are already affected by changing climate and increasingly by non-native flammable grasses that promote huge fires, often referred to as megafires. For instance, the 2018 South Sugarloaf fire in northern Nevada burned nearly 250,000 acres, starting in sagebrush-steppe and burning up into drought-stressed aspen and conifer stands. And the ability of these aspen stands to regenerate after such events will depend on factors such as climate and browsing impacts, but also the health of the stand before fire. So at lower right, for instance, we can see a lower elevation stand that suffers from multiple threats, including heavy browsing with almost no recruitment-sized young trees, an invasion of flammable cheatgrass into the understory, and pinyon juniper encroachment. These conditions could cause more severe or frequent burning, and if combined with continued browsing pressure or drought after fire, the clone may lack the capacity to successfully regenerate, leading to wildfire-driven forest conversion. So, in conclusion, what are the management challenges ahead, and what are some key factors to guide aspen conservation strategies in the Great Basin and beyond? Well, first, we should expect unique responses among different aspen types, functional types, as Paul had referred to earlier, to changing climate and fire regimes. For example, post-fire regeneration responses will likely vary among functional types and along elevation and moisture gradients. We should also expect regional to local scale differences in climate change effects themselves, including patterns of drought, diminishing snowfall or snowpack, and climate-induced fire frequency. And this may present contradictory signals for land managers, and adaptive management approaches may need to be constructed commensurately with this variability. We should also expect the unexpected as novel combinations of stressors become more likely, including unprecedented climate shifts and plant interactions that could fundamentally alter the role of fire and create less favorable conditions for post-fire aspen regeneration. And then finally, these changes could lead to rapid and irreversible change, including type conversion and aspen forest loss. So I suggest we need to better assess aspen vulnerability within different environments, similar to the presentation that Hall had given, looking at FIA data. And this kind of information could help us to prioritize conservation measures that are most likely to be effective over the long term. Oops, there's my last point. And with that, I'll close and just want to quickly acknowledge that some of the funding sources, especially the climate adaptation science centers that have funded much of this research, and our many partners and field and laboratory techs who've participated in our research. Thank you.
All right, great, thanks. That was terrific. I have a question. I'm not quite sure how to phrase it, but I was curious. I mean, they call aspen the asbestos tree. It's not always that easy to get it to burn. But with increasing fire intervals, or a shortening, increasing fire leading to a shorter interval, I'm guessing a lot of that's going to be driven by conversion from sagebrush to cheatgrass. Kind of the idea there. Can you speak? I mean, can you get sagebrush? Can you get aspen to burn from an adjacent cheatgrass fire, or does it really need more large dry stems and conifers and perhaps sagebrush and juniper encroachment, that kind of stuff? I'm just wondering if you have any perspective on that.
Yeah, well, I don't think that's been analyzed yet in the literature, at least not that I'm aware of, but there's been an increasing body of sort of review or speculative types of research papers that have talked about this kind of dynamic. You know, how much are those changing conditions around low elevation montane forests, including aspen, likely to be impacted by changes in adjacent sagebrush? Yeah, anecdotally, I can tell you I've seen isolated aspen stands and low elevation aspen stands that have burned when conditions were right, due to range fires that move up into the forests. So I think with drought conditions, with understories that are probably seeing more of a sagebrush or drier vegetation components, combined with extreme fire weather conditions, that those stands are very vulnerable to burning. And of course, aspen doesn't necessarily need to burn very thoroughly to die. It's susceptible to even low intensity fires in terms of its mortality rates, being pretty high even with low severity fires. So I think those stands are potentially very vulnerable.
All right.